GraphDB. So before starting, right, I would like to ask a quick question. So how many of you are familiar with GraphDB or Neo4j? Quick raise of hands. Okay, there is only one. Okay. Okay, we have one audience who has used GraphDB, right? Like, so what kind of domain you have used GraphDB with?
Domain used is for industrial purposes. So when you're building something in production level, like a hardware building, kind of a hard drive, and there will be a lot of components in the hard drive.
Okay.
To map these components, how these components are interconnected together, and what is the minimum amount of components required for a particular product to build. So one of our clients need these kind of data. They want to explore all these quantities. And that's where I explored with the Neo4j, because it will be a better option for us.
Thank you, Sudan, for the introduction. So we will also be covering manufacturing domain throughout this session, and we'll cover it in more detail. So the agenda for today's session, so we will quickly introduce, so we already saw there are like very few people who are aware of GraphDB from the audience. So we'll quickly introduce GraphDB, then we'll slowly dive into what is Neo4j, and we'll talk about our journey with Neo4j, like how we have used Neo4j in our project and how it has helped us. And finally, like how we could leave the AI flavor in any session, right? So we'll be also covering the Chennai with Neo4j. Okay. GraphDB, right? So when you talk about databases, we normally default to relational databases. So where we have tables with rows and columns. So otherwise, like we go to NoSQL databases like KeyPair, document DBs and all that. So how GraphDB is different? So GraphDB kind of helps us to visualize the data and the way we see it. For example, let's say you go to a whiteboard and you start ideating things, you start drawing things. The same thing can be visualized in GraphDB. And two main components of GraphDB, right? So here in this view that you see here, so we have a product which is sold in different countries and which has different costs. So the product, country, and costs are represented as nodes. And these nodes are connected through something called as relationships. So you'll see more about this in the upcoming slides. Just again, going back to our regular way of doing things, right? Like going back to relational databases. So we have a product which is sold in different countries with multiple colors and different costs. So this is a standard setup that we have seen in many cases. And how these data are related, mostly through foreign keys. How the same data could be represented in terms of GraphDB. So again, we have the nodes and the relationships. So the main difference over here is like here, these data are connected through relationships instead of foreign keys. And the way this is connected, this gives us it gives GraphDB an advantage of a faster retrieval of data. We'll see more about this, like how GraphDB is more performant than relational DB. So in any relational databases, right, we have tables, and how do we retrieve the data? So we use a query language. So we use an SQL where we select certain, just like the first line over here, right? Like we pick up certain columns and from particular tables, and we do a join by using the foreign keys across tables. So when we move on to graph, so there are multiple options to query data from graph databases. But you're going to see one option today, that is ciphers. So as I talked about multiple options, below you could see there are options like Gremlin, SparkQL, and GQL. But here, so Cypher has its own advantages in terms of declarative nature. It has a good rich ecosystem, and it is also optimized for deeper traversals. So that's why here we are talking about Cypher, and Cypher is also supports by default in Neo4j. So that's the reason that we have picked up Cypher over here. So a similar example, right? What you see at the top for SQL. So we have a Cypher query. Okay. So I think we have only one person who have used GraphDB. So I think most of you would have not seen Cypher queries before, right? Let me try to explain. So here what we do is like we have a match statement which checks for products, which has a color. And then you also see it matches the product with cost and country. And it returns all this data. So when you execute this query, you're going to see a graph like this. So the beauty of graph and cipher is that like even though the data increases, the level of depth increases, the queries will still be simpler. So that's the main difference between SQLs and ciphers. So what is Neo4j? So Neo4j is basically, so there are multiple offerings, right? Like when you talk about GraphDB, so here even at the bottom, like I have listed, there are so many offerings of graph databases. So each of the cloud providers have their own offerings. Like you have one from Amazon, one from Azure, and there are other offerings like Tiger and Arango as well. So Neo4j is one of the offerings, one of the most popularly used offerings. And there are a few key features, right? Like why we also chose Neo4j. It has a native graph storage. So what does it mean? So in case of, like offerings from Amazon and Azure, so they basically store the data either in a relational form or in some cases key value pairs. And a layer is created on top of it, which translates this data into a graph form. So when this happens, like when you go for deeper retrievals, the performance will be relatively slow. But in case of Neo4j, it stores the graph the way we see it. So when you go really deeper, the performance is better. And as I said, like we also saw the different query languages for graph, and it uses Cypher by default. So that is also another reason. So in case of Neo4j, like we also have a cloud-based offering called as Neo4j Aura. Okay, I think we talked a lot about graph and Neo4j, right? Let's also see a graph, right? So this is a desktop version of Neo4j, which you could install. And as you can see, for this particular session, so we have set up a sample data for a manufacturing domain, basically an automobile domains where there are manufacturing of items like cars, trucks. And we'll talk about this, right? Like, so here, if you see, there are different nodes that you have created. So you could see a product node, which could be a different vehicle. So there is a country node, so where it could say like how in different countries that it's been sold. And we also talk about assemblies and parts. So we'll talk more about this in the upcoming slides. So this basically talks about how a product is built. So these are some of the nodes that we have. And we also talk about different relationships. So let me just quickly expand this, right? Like, so this is the So this is the complete data setup that we have. So this is very small compared to like what you have in production systems, right? Like, so if you see the, if you'd have seen the number of nodes, like it was only like 30, 40. But in production, if you go, like it'll be in millions. But for simple representation, we have picked up a very simple example. So as you can see here, there are different nodes, right? Like we have product nodes, like bike is one. You could see car, it's a bus. So these are different types of products that we have. And you also see these country nodes. And you see how these are connected. And you also see these assemblies. The assemblies are basically a bunch of parts that goes together to form a product. And what are the parts that are consisted or used to build this assembly? So these are covered in this light blue colors. So looking at this one, right, like as I mentioned, like this is a very simple representation, but even this might be confusing. What I will do is like I'll quickly minimize this and I will show you. Okay, so what I have done over here is I've just queried. So if you see the cipher, so what I have done is like I've tried to get the data, but I have tried to get the data for a car. So seeing multiple products, you would have seen a lot of relationships, you would have got confused. So I have just tried to query a car and you see the graph for a particular car, right? Like, so now I think it looks much better. So let's say it has, oops, okay. So you see a product, which is nothing but a car, and you see different colors that are there and how this is connected through a relationship called as has color. And you also see different assemblies. One could be an interior assembly, like which has seats, dashboards, a chassis assembly, a transmission assembly, an engine assembly, and different countries where they're sold in. So this is a representation. So this is another advantage of going to graph, right? Like even when you see the graph, you can learn from the graph. So let's say if you don't like the graph way of viewing the data and you are used to a tabular form and you would like to see the data in a tabular form. So that is also an option, right? Like here, so the same data. So what I have done here is like if you just compare the cipher. So instead of returning the nodes, like I'm trying to return the property types. So each of these nodes, I think this is something that I kind of missed. Maybe I'll quickly cover that. So if you see in this example, let's say if I click a car, so you see these property nodes, right? Like, so for these nodes, you can also set properties. So have set up properties like a category, when it was launched, what's the name of it, what's the variant. And what I have tried to do in this tabular form is I have tried to retrieve the properties directly. So you almost get a tabular form, a denormalized form of the data in a tabular form. So these are few examples. I just wanted to quickly show you the Neo4j also in action. Okay, so I think so far like we kind of got introduced to graph and also Neo4j and how Neo4j looks like, right? So now what I will start doing is like start talking about how Neo4j or graph helped us in our project. Okay, so when we go for a new solution, like whenever we have a problem. So we were from manufacturing domain and we were dealing with BOM data. So how many of you are familiar with BOM? Any show of hands? Okay. Okay, I see one hand over there. Yes, Syed. Yes. So BOM is bill of materials. What it does is like just like the representation that you see over here, right? The cycle, so cycle parts that you see over here. So bill of materials in the manufacturing world is parts that constitute to form a product. So it will be at different levels. Like it's not directly parts, right? Like multiple part forms an assembly and multiple assemblies forms a product. So that's the bill of material. And so we had an application where the users used to compare the products. So how they used to compare the products? To see the parts, how it is constituted. Why do they do it? Let's say if they want to launch a new product. So what is the combination that should have? So if you see any product in the market, right, like you have a new version and that is better than the previous version, how do they do it? So they go and check what is there currently, what are the parts and what you could do, even if you take a mobile phone, right? So there is a camera lens that is available. So can I upgrade this so that I can get more sales? So these kind of comparisons happen. And initially when we started, like we started with few products that are onboarded to the application. We had a BigQuery database. On top of it, we had a user interface that was built on React. And users started using it. But as we started loading more data, onboarding more products, the performance started degrading badly. And at one point, we reached an instance where it took 20-30 seconds for the users to view the data. Okay, so that is where like we felt we have to do something about it. And when we saw most of the problems was due to the recursive retrieval of data that you're doing. So as I told you, I just showed you an example, right? Like with one assembly and one part, that's like 1 or 2 levels. So at least at that point of time in our product, we had 7 levels of retrieval. So we have an assembly, we have a part. And then that part, let's say like we have a battery pack. You have 2 batteries inside, you have a battery covering. So then you have a screw that ties in. So this level keeps on going inside. So when the query becomes really recursive and when we have so much of data, it was taking more time and users were not happy with it. So I was talking about this BOM data, right? So forget about complex products like a mobile phone or a car, right? Like take something as simple as a cycle. And even in that cycle, so if you see, I have just highlighted the tires or the wheel assembly, right? So wheel assembly is the most simplest thing that you could think of. So here what I have tried to do is like I've tried to break down the wheel assembly so that I could explain the complexity of hierarchy that you have in manufacturing products. So if you see, like I take cycle as an level 1, right? So if I take level 2, so there could be multiple other assemblies. For example, here I have just mentioned 3 assemblies, like We could have a brake assembly, we could have a wheel assembly and handlebar. There could be numerous more assemblies. Just for representation, I have given these three. So then let's try to expand the wheel assembly and see like how deeper it could go. So wheel, when you say a wheel, it could have a tire. And when you say a tire, it could have a tube inside the tire. And when you say a tube, it could have a valve, right? Like where you kind of fill the air. And when you say a valve, that's also not alone, right? Like valve has a brass core in it, if it has taken it out, and it has a rubber tube that's connected to the brass. So on top of that, you have a cap that fits it in. And this level doesn't stop here. So it also goes much deeper in like, okay, what is the raw material that is used to build that small tube? And what is the raw material that is used to build the brass core and all that? So it goes really deeper. So this is how deep we have BOM data for a wheel assembly. Just imagine complex product. Let's say you take a car, right? Like how many parts that you have, how deeper it could go. So this is why we had this challenge. So when we had we had millions of records. We had around 3,000 products that was on board, and we had millions of records, and that's why we were facing the problem. And Neo4j came to the rescue. So we didn't just pick up Neo4j just like that. So we did an analysis, and we found out that the problem was with the BigQuery and the recursive retrieval of the data. So then we figured out that like this is one of the standard use case, and it is also used across multiple manufacturing domain companies, right? Like, so we tried exploring it. We did a spike. So I'll talk about the spike data in the next slide. So we did a spike, and it worked well. So then we started migrating the data from BigQuery to Neo4j. So there it was all tables. So here we started migrating them to nodes. I have just given few examples, right? Like products, assemblies, cost countries, and different relationships. And Neo4j was a perfect fit for us. Like if it is recursive traversal, so this was really helping us, and which was giving us faster queries. And the addition was also the graphical visualization, right? So when we explored this, we also explored the other GraphDB offerings like Amazon, Azure, as I already talked about. So for us, like Neo4j was a best fit because we wanted a database with native graph storage and also with Cypher. So this kind of fit well in that scenario, and we went ahead with Neo4j. So this is the sample representation of the output of spike that we had. So I talked about the different levels, right? So at that point of time, we had level 7, so maybe at a screw level. So we had plans to go even deeper. Let's say we have a plastic part. So what is the resin material that is used to build the product? So we had plans. And already we know that like the data is going to grow exponentially. And even with the current state, this was not helping. And this would have never helped when we expand. And when we did the spike, like we kind of compared the BigQuery data and also the Neo4j side by side, and this was the output. So in case of, for a depth of 2 levels, right, it was like lesser than 2 seconds. And all this with 3,000 products and with millions of parts in that, right? Like it's not just few parts like the example that I showed. So with that kind of a data, like we had 2 seconds for 2 levels and 15 seconds for 5 levels and 40 plus seconds for 7 levels. So this clearly shows that when we go deeper and try to retrieve the levels, like the time was increasing exponentially. But the same thing when we tried with graph. So for 2 levels, it was only 150 milliseconds. And even there, it's not constant. It was increasing, but it was linear. It's not as exponential as what you could get in BigQuery. And even for 7 levels, like we were able to get that in 600 milliseconds. And with this, after migrating this, like our system became better and there was no lag. And we started kind of expanding further. So for the data size for this spike that we used is also like 5 million nodes and 10 million relationships. So this was the data size, and this was the performance that we got. So with this, like we went ahead with Neo4j. So this is a story from my project. Having said that, right, like, so I have shown like tremendous improvement in terms of the performance, right? So do you feel that like you can just go back to your project and get rid of all the databases that you have and switch to Neo4j or a GraphDB? So each database has its own purpose, right? Like, so we need to see. So now we kind of got introduced to GraphDB, but we also need to understand like where it makes sense to use it, right? Like, so These are some of the examples that we have. So where we wanted to point out and show it to you. So for example, manufacturing is one domain that we have clearly seen a very good example. So apart from that, like if you want to see social networks, right? Like let's say Facebook. If you go to Facebook, like you will see your friends of friends, their friends. So how all this is managed? Using a graph. They don't use Neo4j. I think Facebook has its own implementation of a graph, but that is again graph. So in recommendations, right? Like e-commerce, streaming services. You go to Amazon, you buy something, like you open and you see all related products. So that again, graph is being used. You go to Netflix, you get all recommendation based on your past history. So that's another good example. So the next we have is also knowledge graphs, right? Like so Google is well known for it, right? Like so if you go do a search, you get all the relevant recommendations, ads related to that. I mean, knowledge graph is again a big topic. I know that Uday, when he comes here, like he will talk more detail about it. So the other thing is networks, right? Like say, if you look at an office, right? Let's say just look around the office and see like what you see more. What? Monitors, devices. More importantly, the wires. See, all the wires you see, 80% of them are concealed. You still see a lot of wires, right? When it comes to networking, so that is also something, one of the complex domain that we have. So networks could also be represented using graphs. So that is also another good use case. So these are some of the examples that I had, like from the audience, like anyone wants to share any other example where you feel, right? Like now you got introduced to GraphDB. So are you able to think of any other example where you feel graph could be a better fit? Anyone from the audience?
Talk about the game space, right? So multiple possibilities for the game to take a different turns, right? And when the ball moves to the different play, the possibilities keep contained in a different possibilities.
Awesome.
So there is a huge number of possibilities, like permutation combinations. So I think it may or may not.
Yeah, gaming could be one. Anything else? Yep. It's in the field of science again. So now we saw like when to use a graph, right? So it is also important, right? So this is even more important, like when not to use graph. Because most of us will know like all these examples and you start, I mean, like after the session, you might be motivated to go back and start using it, but you should understand when not to use graph. So I have few examples again for it, right? So basic CRUD operations, right? So graph is mainly for data that has complex relationships. So if that is not the case, like it doesn't, if you just have basic CRUD operations, right? Like you have an employee database where you just maintain the records of the employee, it really doesn't make sense. It will still work, but it really doesn't make sense to use graph because it's an oracle. And where you have large amount of data, like a sales data, a warehouse thing, again, it doesn't make sense. And also places where there are high transactions, right? But the data is simple. A very good example is a trading application. So you have millions of trading happening on a daily basis. But if you see the data, it's not complex. It's the structure of the data is very simple. Then the other areas like where there is high writes and then less querying, right? A very good example could be IoT. So you have an IoT device placed somewhere, a temperature sensor, and it keeps giving you the information every minute or every hour. It's so much of data, but it's a simple write, and it's going to keep writing, but you're not going to do a lot of querying over there. So these are some examples that I have where it doesn't make much sense to use graph. So any other examples from the audience that you want to share?
You have two perspectives. One is as you said the right, and the other perspective is the view. This comes again of the networking. Okay, so do you think that part can be still use the graph data, graph.
Okay, so the question here is like IoT for the viewing part also, like you could use graph for networking, right? So it again depends upon. So if you just want to know the status of it, querying it doesn't make sense. But if you want to get insights out of it, then you want to form relationships, right? Okay, like so let's say you want to understand, okay, at this particular time the temperature is like this. So at 1 p.m. in the office, suddenly the AC temperature goes up and everyone. So why this is happening? So if you want to investigate such things and gain insights out of it. So then the data becomes complex. Otherwise, like if you just want to know the status, right? In most cases, IoT, like you want to know like whether the status is red or green, right? In such cases, it doesn't make sense to go with graph. Any other examples? Yes. Yes.
So initially, when the project comes in, the scenario is simple. So as you said, just know the status of the LVDS. Then business goes, and then scenario goes. Now we want to view the insights of the video. So now we switch from the normal TV to graphic video. So is it okay to do that or continue to use the normal TV?
Yeah, looks like Sudan already has an answer. Yeah.
Just in theory. So in that part, right, you have two different systems. One is as right, it's a port of them, right? The second thing you need to don't need to the entire so you need to have the graph DB only for analysis. So you need to have a redundant of data, but after as you said, when the business grows, you need to if you're switching to the graph DB, then again this situation comes and like.
See, the basic idea is like start simple, right? Like if when you start, like you never know, because even when we started, we never had the idea of using a GraphDB. So we used SQL and we faced the problem. And to solve that, we brought in GraphDB because GraphDB also has its own cons. Like it comes with a lot of cost. If you go to offerings, like it's, I would say like easily 4 to 5 times or even more than that compared to an SQL. So if when needed, you can start using it. Until then, like I think you could just stay with what you have. Yeah, okay, quick time. Okay, so just a quick recap. So I think in the beginning we kind of got introduced to GraphDB and we saw Cypher queries and we saw Neo4j. And I also kind of introduced you to how it helped us in our project to get rid of the performance issue that we had. And then also we saw when to use it and when not to use it. So a quick recap of what we did. So what next, right? Like, so how could we leave this topic, right? Like, so whatever presentations that we have and whatever we do have, unless we had an AI stamp, it's not complete. So let me pass on the control to our AI expert, Uday, to take it further.
Okay, so this time it's not just a stamp. So we are going to see hands-on about how Neo4j is enabling the GenAI ecosystem. So first of all, how many of you are comfortable with the prompt engineering? Can I see? Right. Okay, cool. Okay, I will quickly cover for people who are not comfortable. So, question to Sudan. Okay. Okay. Okay, fine. Sudan, are you a vegetarian or a non-vegetarian? Okay. The answer is pure non-vegetarian. Okay. So what I have asked is, I didn't ask a question. I actually prompted him to give the answer that I am expecting, because I don't need to know what he ate and what are his favorite foods, nothing else. Okay. And I was expecting him to answer clearly between the given choices that I have provided. Okay. So that is exactly prompting. And consider the same scenario when we are interacting with a Copilot or a ChatGPT. We are going to ask something and we are expecting an answer for that. And the system on the other side is a kid. We have to explain everything. Okay, you are having this persona, and these are the inputs, and this is what the situation I am in, and I am expecting this in this format. So in how much detail that we are able to interact, the better answers we will receive. So that is about prompting. And okay, the next level. So with GenAI ecosystem, there are 3 steps. So first one is how many GenAI tools that we are using for our day-to-day thing. So the first one is usage, and second one is understanding the ecosystem, and third one is developing our own tools in GenAI. So these are the 3 things. So first, to get into the ecosystem, we have to use the available tools in a better way, because even with ChatGPT in our being available, we can use it in a much better way in our day-to-day things. So consider a life of a project manager. So they would be using in their day-to-day life, they used to face a lot of things, a lot of data to understand and other things. So you can see that it has been enabled even in Jira and Confluence recently. So every tool that we are using. Okay, it looks like it's raining. Which one? Okay, cool. So every tool, Excel, Confluence, Jira, and encoding. So everywhere, tools are available. We have to use them in a better way. So that's the first level. The second one is trying to understand for a given problem, is it a problem to be solved by a GenAI or not? Because GenAI comes with the gen in the first, which is generation. So is this problem supposed to be solved through generating something, or is it just a classification problem? So that's where the difference between classic AI and Gen AI comes into play. So many things can be solved with classic itself. So there we don't need to go for a Gen AI. So if someone is over engineering, it may end up in that. So that's the second part. We have to understand the ecosystem. And the third one is what are the tools available for me to solve it in a better way. And Neo4j is one such tool, and how it is enabling the solving of the problems. So we can see into that. And how many people heard about RAG? RAG, Retrieval Augmented Generation. Okay. Okay. So it is a flow of a RAG. You can see that when we interact directly with LLM, that is first level. LLMs are already pre-trained, and it can understand language, and it has some level of reasoning into it because it occurred through the large amount of training data that it has been trained on. And we can interact in the normal language, and it can give reply. So that is the first level. And the second level, okay, all the data has been used for training, cool. And mine is an enterprise one. And I want to keep it with myself. I don't want to build that into a model. That means model is portable. Anyone can take it and use it. So I don't want to give that thing. I want to keep it with myself. And I want to use that along with the LLM. LLM should be able to read my data and provide an answer based on my data. So there comes the RAG, Retrieval Augmented Generation. That's generation will be augmented by retrieving from the enterprise data. So this is the flow where user will be actually making a call. And first level, instead of directly going to LLM with the question, we would be first look into our knowledge base. Our knowledge base will be set up based on our data, and there we will make the first search, and that is a vectorized search. So the text will be converted into vectors, and vector matching will happen. Okay, what is a vector matching? So we have consider a paragraph on fire, and that will be stored somewhere in a format. And there is a question coming up with something related to lava. Okay, so this question will actually have some probability of matching with that paragraph with fire, because it talks about same things. So this matching probability that allows this filtering of relevant documents. The moment we retrieve the relevant documents, when I mention about vectors, vectors are used just for the matching. But after that, what has been actually consumed from the documents is an actual data. So vectors ends after the matching happened. So it will be splitted and it will be actually a key value pair saying, okay, this is the embedding, this is the chunk of data. And these are the, so that mapping happens. And for a contextual mapping, we do know that there is a string to string map. And the next level is similarity, semantic match will happen. And now context-based map, saying when I am giving 3 paragraph, the second paragraph may have more meaning after reading the first paragraph. So that contextual also being captured in the embeddings. And based on that embedding matching, we will be having a more relevant data. And the data is an equivalent text. So that equivalent text will be taken and it will be appended with a query saying, this is the question and this is the data from my knowledge base, and LLM, make sure that you are answering within the context that I provided. So you don't come up with your own learning, keep that aside, and answer only from what the data that I am providing you. So when we are saying that, LLM will actually update its response, provide the response based on the data provided. Again, prompting. We are asking it to provide an answer within the given context. Then it will indeed provide that. Else, it will hallucinate. It will have its own data, and there's high chance that it may hallucinate. Okay, so it's a general RAG. And we were saying about this knowledge base, right? Let's quickly see what that, how the knowledge base has been created. Okay, knowledge base, yeah, we have our Confluence pages, and we have our FAQ documents, product documents. So all documents may be there. So all of them are our knowledge base. And the first step of the vectorization is those, whatever format it is, PDF, text, or even a web page, it will be taken and loaded into a document, and the document will be split. It will go through the splitter and it will be split. Every document will split into multiple based on the number of, that is on us. Based on how much of a context the LLM can take or should take. Because if LLM can take only 100 characters or 100 words, it may not be enough for us. That could be one case. And if to get a proper response, we need to provide 1 million words. That means I will scan the entire PDF and I will send the entire thing along with the query to answer better. So in that way, the number of tokens will be heavy. Even a single call will be much more costly. So that is also not feasible. So we have to come up with that sizing, token sizing. So what is that number of words that I can accommodate in a single split? So that is on us. So after that, that would go into an embedding logic to convert into embeddings. So every chunk will be converted into equal embeddings, and those embeddings will be stored, and we are storing them in vector database. Okay, what are these vector databases? So we'll see that embeddings, how it looks and how it is being stored. Okay. We'll quickly see a demo of RAG as well. Okay. Okay, you can see that, okay, this is RAG, again, the same illustration over here. So considering the time, I will not go step by step, but I will explain the steps and we can see how it looks. So these are the, here we are using ChromaDB. So ChromaDB is a vector database. It's like a SQLite. It's a lightweight in memory. And we are using Google Gemini API, and we are using sentence transformers. Okay, so we are using these LangChain text splitters. So these are the libraries by default available, so we are using it. And then what we are doing is we are going to get this data. So again, I am going into automobile industry, saying what are the luxury cars available in India. And so this is a blog about luxury cars, and it has around 7 luxury cars. So what I did is I copied this blog content, and you can see that I just removed, okay, you cannot see this, fine. So I just removed the images, and I have all the other text in it, fine. And what we are doing here is we are just reading that, okay? Here it's just a read, and we are going to read the, after reading the data, that is the document. So we have read the content, and we are going to split it. And how am I going to split? I'm going to split with the size of 800. And this is chunk overlap is 100. That means the first chunk will be character 1 to 800. The second chunk will actually start from 700 to the next 800. So there is an overlap so that the words sentence will be complete. So for that, we are using this. And after splitting, we can see that that has been splitted into 34 splits because this entire blog is there. And after splitting, we have converted that into embeddings. Here, it's a sentence transformer which has been used, which will go with Google Gemini. And after the transformation, this is the blog embeddings. And what we have done is we have listed the text and the embeddings. So if you take this text has an equivalent embedding like this. And when we are doing a embedding mapping, if someone is asking within this text, a question lies within this text or somewhat relevant to this text, there is a high chance that this embedding will get mapped. Okay. Now, after that, we will be storing them in a ChromaDB. So you can see that these are the embeddings we created and these are the chunks. That's the one-to-one mapping, the key value pairs that we are storing over there. And it has been added as a collection. And this is ChromaDB's concept. Finally, what we are doing is we are making a vector search. So this is where the mapping happens. So how the mapping happens? The question, whatever been asked, will also be converted into embedding. So the mapping actually happens between two embeddings. Question also be converted, and that's what is happening over here. And the query will indeed be encoded, and it will be passed over as a query embedding. Then the search will come up with the result for this query. Okay, we'll see the result along with the actual questioning because vector mapping alone happens over here. That means this is the chunk which has been mapped. So we just received the chunk. That means in our cycle, we are here. So still we are here. So we didn't use the LLM at all. So we are still within our own system. Embedding creation, we do use. And that is not a complete LLM. It's a smaller models will be enough. And give me a moment. So the next one is, okay, so this is a model querying, and here is a prompting. We are setting the context. you have to make sure that answer within the context. Then here comes the actual question. So the question is, okay, what are available in Mercedes? So that's the question. And we do know that there is an entire paragraph about Mercedes over here. And it says about these models, and they are inside. And we do know that the size is 800 tokens. Token is something similar to a word, but there may be more number of tokens per word as well. So how it is, let's see how it answers. Okay, it is mapping this. And it is saying that the key features of a Mercedes-Benz. So the question actually is, what are available in a Mercedes? So we didn't say about a variant. The question is rough. And what are available? Okay, it has these and these features. So that's a understanding, and that's how the answer came. Okay, now the next question, let's, okay, give me a moment. So what are the car brands discussed in this blog? So that's the next question. And let's see how it provides. It has mapped one, and in this particular chunk which has been mapped, we know that only Mercedes is there. I mean, LLM knows that only Mercedes is discussed in that particular chunk which was mapped. But that is not entirely true, because in the entire block, we do know that there are 7 of them, but only one is available. And okay, this is very basic RAG. We can improve it by adding the number of chunks that we need to choose. So I have added as 3. That means don't take one chunk, take more than one. Take exactly top 3 and send them along with the LLM and see how it answers. And when we are sending that, so this is actually 3. And here it says there are 6. Because if there are 3, it was able to cover 6 of those brands. So we will end up having more context then. That means sizes keep on increasing. So it is a simple block. That's why it is happening like this. But there is a medical book and we want to use the entire book. Then we will end up with that more costly approach of send everything in the context for every call. So that may not be an optimal one. So that's where we will go to our next possibility. Okay. Through graph, how can we address it? And graph do address this in some of the parts. Let's see those parts. So knowledge graph has been around us for a long time. And everyone see these, know this Google search, and daily we will be experiencing this. And knowledge graph has been used by Google. So there are questions here. Which part is driven by knowledge graph? Anyone guess? Okay. 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 The right bottom. So when we are, yeah? Ask for. Okay. Anyone? So search engine. Entire search engine. Okay. 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 Before jumping into it, can anyone guess the time in which year knowledge graph has been used by Google? Rough guess. 2004. 4 and 5. Okay. Sorry? 15. It is closer. So it's 2012. We do know that LLMs also being driven by one of the papers which was published by Google about all matters is context. Similarly, knowledge graph in 2012, there was a blog by Google. So I just added it over here. So it's a they have brought this saying things, not strings. So it is a transition on the search engine side. So we do know that we use Lucene, Elasticsearch now for matching with text. So that string matching is a thing. And after that, it has evolved into semantic mapping. So semantic search was a thing. And now then it has evolved more into, okay, not just with the meaning, I like to know things around it. When someone is calling out my name, they may want to know my interest, my relations, and who are my peers. So when you are considering about a company or a product, what are the similar products, or what are the latest news about them? So all these things, they might be interested. So it's not just a string mapping needs to be provided as a result. It has to be a thing mapping. So that's where it has to be stored in a way, then only it can be provided in that way. So knowledge graph was used in that space, saying there is a Neo4j as a node, and it is a cluster. It comes with all different other nodes being connected with relations. So when someone is searching for it, look for that node and bring all the data and map it and show it effectively. Instead of doing a string mapping into all the place and in B-tree matching or any other algorithm, store it this way, then retrieval would be easier. So there is one thing in Neo4j, when you are thinking about modeling, Neo4j data modeling should be driven by the need of the querying. So it has been designed with nodes and relations for a reason. So if that is the need for you, then you have to store it that way. So similarly, why are we going for a knowledge graph? Because we need to get those data in that way together. Then people go for a knowledge graph. Okay, now let's see how this knowledge graph. So this transition of a search we have seen. Normal string, semantic, and then as a knowledge graph with the entire knowledge around it. So the similar thing happens in RAG as well. In RAG, we do map the context of a paragraph. I have a paragraph, I have a question, I will learn the question and I will convert it into some embedding, and I will try to look for a probable matching, or the top 5, top 10, I will take and I will send it. How is this mapping happens? With the context only in that paragraph. Now, if we are able to store more around it, then will the results be better? It might be. Because when we are going through an entire Constitution of India, so there will be a lot of things, and we are able to map everything together and have a relation. Then when someone is asking about an article or a case number, they can indeed get everything related to it. If they are going for a paragraph by paragraph mapping, they might not be able to get all the details. So on such occasions, storing them in that way actually helps. So that's the transition of a RAG. So textual RAG, so contextual, and then a knowledge-based graph RAG. Okay, let's see. Okay, it's just a representation mapping saying how Apple will be viewed by us, and the same thing in vector. We saw it in a demo. And when we are saying a knowledge graph, things about the apple, which is what is its structure and where it comes from tree, and it's a kind of a fruit, and it has a color, size, and shape. So this is the node of an apple comes with. Okay. And how is the RAG lifecycle updated with a knowledge graph? The thing is, still user asks a question, and we will go for a graph retrieval. So based on the question, we can even use LLM for that. Okay, this is a question, and what are the entities that I can look for? So for that, we can use LLMs clearly, and we can look for such entities and bring all the properties around that entity or connects around that entity. Okay, I took all those things. Now I have a better data. So can I give this data along with the LLM? We can. And Neo4j also provides a way of storing vectors as well. So in a node, we can indeed store a vector itself. So along with these relations, we can say that I am getting all these relations, and this indeed available in this paragraph as well. So along with this graph and relations, we are actually going with a source. This is a relation, and these are the 4 paragraphs where I actually created this from. So when we are sending along with this, we will get much better results. So that's what knowledge graph being used in a RAG. So it's document and context being shared. Then while prompting, along with the question, we will be sending those actual docs and the context from a graph. Then that's what we receive is a complete response. So it's a better response. So what we get out of it is 2 things. One, the results will be better than just a context-based mapping of a particular section of a document. And the second one is it is better explainable when we are able to debug something. So we can see that, okay, these are the results that has been passed along with this question. So instead, if we are passing it as just a chunk, it will look like this is a question, this is a chunk. Okay, this is a chunk. So, but when we are also providing the entire object along with it, saying, okay, these people asked about BMW. This is a BMW, and these are the data that I have captured and I have provided, we can easily debug. Okay, this didn't capture that part of the book. Then we can update those graphs on that side. So it's auditable and it's explainable. Let's go for a demo. Okay, I can quickly go over it. Fine, so here I am actually using a Neo4j. This is a Neo4j Aura. It's a free instance of Neo4j that we are using. And I'm using OpenAI here. And I am using exactly the same data that has been used. Okay. Now, we saw about the loading part. So we are just reading the data. And this is the raw document that has been read. Okay. And here, the next step would be splitting. We just read the entire text. Now we are going to split it. Here, the splitter that we are using is token text splitter. So it's a token-based splitting, and chunk size is 512. I'm going for an even smaller one. So in the previous RAG, we were using 800 and overlap of 100. Here, I'm using for a more granular one, 512 and 24. And it was splitting that into 7. Fine. And the next step is we can convert that into a graph document. Okay, there is a paragraph, and I want to create graph nodes from this paragraph. Then we can indeed use LLM. I said that we can find what are the entities in the paragraph through an LLM, and this is that. So there is a LLM graph transformer, and we are using the LLM. And the document created is this. And what are these documents? It has notes. You can say that there is a type car brand, and ID is Mercedes-Benz, BMW. So these notes has been indeed created out of the paragraphs. Fine. So graph nodes has been created. So now we have to store them into Neo4j. So Neo4j should have that capability. Yes. And we are storing them into Neo4j. Cool. And how do they look? This is how that look. Hope it is visible. Yeah. So I can see that there's a Mercedes-Benz. It has a model C-Class, E-Class, and a Maybach. And there's a highest selling GLC. So this has been taken out as a relation from that paragraph. When someone is saying things in a paragraph, it has been converted into an equivalent graph. And we can see that this is Mercedes, and we have Rolls-Royce and Bentley. Bentley has less data, and Audi. So this is how this has been converted. Okay, cool. So that's a nice, good graph document, and it has been stored. And we mentioned that we just won't give the relations. We will also give an equivalent text. Okay, then the text should also be available. Yeah, there is a embedding node property called embedding itself, and it indeed will create a node called embedding with embedding data in it. We'll see that in Neo4j itself going forward. And we are going to query that, and we even have a chat history over here. Now, let's, so this is a retriever. There are two kind of retrievers over here. One is a structured retriever. Structured retriever will look for mappings within the Neo4j. Okay, there is a question, and related to this question, what are the nodes and its relations I have to provide? So that's what structured retrieval will provide. And when the question is about what are the offerings from BMW, it indeed provide these nodes and relations. Okay, BMW operates in BMW India, and it has successful models. And these are the models with the model relation, and it invests in electric vehicles recently. So these are the things observed from the paragraph and stored. And when we ask about a question, okay, these are the related. So this data is available. So this can be passed along with our actual text data, and it indeed can provide better answers. So what are the brands discussed? This is a question that we asked in the previous one, right? So let's try to run it over here. Okay. Okay, it says brands discussed are 1, 2, 3, 4, 5, 6, 7, 8. Okay, there is a Land Rover as well, Jaguar Land Rover. Oh, okay, 7. So 7 things over here, and how it come up with this is it actually fetch based on this. So what are the car brands? So there may be something called a car brand as a node, which has been given and collected as an answer. And we can go for one more step, saying I just added over here. So what are the brands discussed? And I just added the okay, the similar one last time. So the question now is list the variants provided in each brand. So the question is, give me the list of variants which are available in each brand. For Mercedes, it may be GLA, GLX, E-Class, E-Class, and for BMW, I series, E series. So give me all the list. So it's not a direct question, right? It may not be available in a single paragraph. It has to go through the entire document. So this question is being framed that way. And let's see how the response is. Okay, I'm just copying. Let's go to this, and I can paste it. Okay. Okay. I cannot zoom it immediately, but yeah, it says all the 7 has been listed. And in all the 7, we can see that list of things has been, we can see it better here. So it actually able to provide all the 7 and their variants because it was able to capture across the paragraphs. So that's, yeah, that's it. This is how it was able to provide a better results over a normal RAG. Yeah, we can. So prompt that was being sent. Okay. Okay. Wait a moment. Is it actually going to this? There would be structured and unstructured that we can see. As a structured retrievers result over here and unstructured over here. Okay. It may need to be aligned as well. Okay, it has unstructured data result being passed. Okay, let's check the next one as well. Okay, so here you can see that this is the structured data result that has been passed, and there is a unstructured data result.
So when we were using vector DB in chunks.
Yeah. Not the, yeah, chunks of an actual text. Yes. Yes. Along with the text.
These relationships, right? So that's what is being added. Obviously, we have a lot of chunks, so we're not able to connect those chunks. Right? So here, with graph, what is being added is like we are creating relationships between the chunks. Okay. So that's why the variance data, which was spread across the page, was very hard for the vector to figure out. But in case of adding the graph, it was able to connect it. Okay.
So we can see it over here. So it's an actual Neo4j DB that has been populated with this data. So this is the database this query is happening on. So we can see that there is something called a car brand and automaker and company. So it's not from the paragraph. So companies has been divided into car brand, company, and automaker. So, but when we are actually calling it with LLM, LLM will be able to actually contextually map it with all three of these and able to get the data.
I think the relationships plus the chunks.
Yes.
The chunks count be larger because more entities are involved now.
It could be.
Chunks
Yes.
larger.
It could be. And here as well. So whenever we are using a LLM, every token counts. So how much better we need the response? So it's in our hands. So we have to restrict it. As good as possible should be enough, because higher tokens will always be a good result, but good enough result should be enough. So on the cost side, we have to be careful on that as well. And here we can see that there is a Jaguar, and Jaguar has been mentioned in this particular embedding. So we were saying that we can indeed get in which embedding this has been mentioned. So when there is a question about Jaguar, so when Jaguar node is being hit, we can get the embedding in which this has been available, and it indeed will take the actual paragraph that's mapped to the embedding. So this is how, and as you mentioned, there's a chance that for all the nodes, when we are trying to get the mentioned embeddings, the number of paragraphs may increase. So we have to be conscious on that as well. Okay, cool. Any other questions? Okay. Thank you. Thanks, everyone.
So we have some more time. We're still waiting for the food to arrive. So I just thought of sharing another story from our project. So I think the first part that I covered was mostly about how we introduced Neo4j into the project and how it helped us to improve the performance. I believe Uday covered on the rack part of it, right? So we also tried GenAI in our project to solve another use case. Just wanted to quickly talk about it. Initially, I talked about how users use this application to see different configurations of products and how they could come up with new products or new versions of the products. So the other challenge that we had was cost optimizations, right? Like when you create products and you get parts, you'll have multiple suppliers who are supplying the parts. So there could be one supplier who's supplying a screw for 10 cents. There could be another supplier who could give a screw for 5 cents. So when you talk about this amount, it might look very small, right? But if you look about the number of screws that goes into a car or any automobile, right? Like then if you calculate the number of sales value that or the production amount, so it goes into millions again. So we were trying to optimize the cost. But the main challenge that we had was the users have to spend weeks to go through all the combinations of products to figure out alternate parts that are available at an optimal cost. So we were trying to solve this using GenAI. So how we did it was using OpenAI integration, but we didn't integrate or model based on the data. Model or train the models based on data. So what we did was we trained the LLMs based on the model of the graph. So how the graph is structured, how the relationships are built. Based on this, we created a chatbot which created cipher queries. So then I also have the ability to create, let's say you go to Chat GPT and you ask for an SQL, right? Similarly, you can ask for ciphers also. But what it needs to understand is like, what is the model, what is your graph model, so that it can create queries accordingly. So what we did was like, we created a chatbot application and trained the model based on the graph model that we had. And whenever we needed any data, a user can go to the chatbot and ask, okay, this is the product that I'm looking at, and how do I optimize the cost of this particular product by replacing a cheaper part? And when they ask this question, so based on the training that has happened, it will generate the cipher query. And it will give us a cipher query. So we are not leaking the data outside our network. It's just the model. And our application used to execute the cipher query and then get the output. So which was taking weeks for them to figure out. So which turned out to be in 15, 20 minutes. But this is still, I'm not on production. We are still figuring out like how to improve this. But this is another use case like where we have used GenAI along with Graph. Just wanted to share. Anything else that?
Thanks for joining.
Okay. So I think just to sum it up, right? Like, so we mainly wanted to talk about how graphs could use, help in performance retrieval, especially when you're talking about deeper related data. And also other important aspect was the knowledge graph, which I covered. So with this, I think we could conclude. Thanks, everyone. Thanks for your time.